Thanks, Vadim. Also, I would like to start by thanking the organizers for this opportunity. It's a great event. So this is work done together with Tomohiro Sasamoto in Tokyo and his students Yori Hiki and Masato Usui and my students Ying Chen in Melbourne. The work that I'm going to talk about has been published in physics literature, PhysRev Letter, and we're still writing up technical details. And like Alexei's talk, there'll be some scary formulas somewhere. But really, the sort of the crux of the argument is quite a subtle thing. So I do feel I need to show them so you can appreciate some technicalities. All right. Just because the audience is a little bit mixed, I just want to give a bit of motivation, and the previous speaker has done that and earlier speakers before, so some of these things look very familiar from other talks, but probably useful to repeat it anyway. So the main setting is this KPZ scaling, for which we want to develop mathematical models that we can analyze in great detail, but this is sort of the physics application, right? So you have a growing of a surface, and this could be a coffee stain, for example, by absorption of some gas particles. You'd like to describe this. And so this was done in the...
This picture is from some particular article?
Yeah, but I forgot which one. I can find it if you... I mean, this has many different types of effects, right? So you have to make some assumptions. So this was done in the 80s by these people, Kadar, Parisi, Zhang. So they developed somewhat like a minimal model to describe this growth in terms of a PDE. And so they made assumption that the growth is random and it's normal to the surface, and that then leads to this nonlinear stochastic PDE. So basically you have a type of heat type equation where the rate of change of the height of your surface that you're growing has a diffusive component, and then it has this nonlinear component which corresponds to this growth normal to the surface. So when particles adsorb, there's sort of a normal direction. So that leads to this term. And then you add Gaussian white noise in space-time. And sort of this is necessary to correctly describe the fluctuations that are in the physical system. So this is a very effective heuristic type of equation to describe that growth. And it's been very successful, as we know. So the claim is that if you have diffusion plus nonlinearity plus space-time Gaussian white noise, you correctly describe 1 plus 1D surface growth, including correct fluctuations. So if you leave out randomness, it's just deterministic, you won't correctly describe the fluctuations. And because I work with Tomohiro, so he's in Tokyo, he has a collaborator at the same university, just a few doors down in his lab, and they realized sort of this growth in liquid crystal. So this is Takeuchi. If you have a chance and go there, you should meet Takeuchi. He's very energetic and he's a nice guy, and he'll show you his experimental setup. Okay, so what are the results that you get out? And again, this you've seen this before, but I've sort of tried to clean it up a bit. One of the main statements is that there's out of this, if you look at the growth of the surface, it's linear in time, but the fluctuations around this linear, the main drift, are of the order of t to the 1/3. So these are non-Gaussian fluctuations. So that's one of the main interesting parts that comes out of it. So while the ingredient is in the PDEs, Gaussian white noise, the outcome is a non-Gaussian type of fluctuations. And so how do you derive that? So this is schematic. One way of doing it is to transform to the stochastic heat equation. So basically you take the z is the exponential of your height function. You get this stochastic heat equation. And then you can write down formulas for the Laplace transform for this z, so the exponentiated height, because it can be written as a Fredholm determinant. So here's an example. If you take the generating function for z at the origin, but as a function of time, so e to the negative zeta z, where zeta is a formal parameter, this can be written as a Fredholm determinant, as we saw in the previous talk, or in many other talks. And then this kernel sort of looks like this. So I've left out a lot of model-dependent parameters to just show you the main parts of it, and not. So there's an airy kernel here, and then this bit corresponds because we're looking at a generating function. And then from this, you can derive that the fluctuations of this height, if you subtract the linear drift term, are of the order of t to the 1/3, and if you then divide by that, you can actually compute the distribution, and it's a Tracy-Witten distribution in this case, for example, or by grains or similar type of distributions. And also, of course, this depends on the initial conditions that you use, right? But I didn't want to go into that. So just sort of a sketchy idea of what are the main ingredients. Okay. So I'd like to talk about not about these growth models, but about the stochastic particle models. And of course, we don't want to be heuristic. We want to go from first principles, define a model, and then rigorously prove or derive these type of formulas. And the setting I will be working in is one similar to this ASEP, which we've seen many times as well. So this is basically the definition that an ASEP on the infinite line here, just a configuration of particles that can hop to the left with some rate p or hop to the right with some rate q. And so you can describe it like this. And so the type of quantities that you're interested in such a model are the current, for example, the main current, and the distribution of the current. So you might just look at a certain location here, just count the net number of particles that cross over time. That's a current, and you'd be interested in the fluctuations of that current. So one way to compute that is to look at this particular quantity. So you take tau as the ratio of the hopping rates, p over q, and define q at position y as tau to the number of particles that have crossed over time. And then you do an even you take like a discrete derivative in tau. So it turns out that this particular quantity is sort of easy to access mathematically. But once you know the distribution of this, you can then get the distribution of this n, which is the physics quantity that you're interested in. So how does that work? Well, it's possible to write down an expectation, a multi-point expectation. So if you look at this, basically the current encoded in a certain way at positions x1 to xk, then the expectation of that quantity can be written as a multiple contour integral in this way. So this was one of the formulas that Alexei Borodin also showed. And it looks a little bit scary, but you get used to these type of things. And the least scary bit is this bit here. This is just a product from 1 to k, because you're looking at k, the observed at k different points. E to the negative lambda t, where lambda is basically the eigenvalue of a transition matrix for one particle, and then some rational function that's apparently needed. And then there's a Vandermonde determinant divided by a tau-deformed Vandermonde determinant, if you like. And this arises because you're looking at an interacting system, so it can't be that all these moments are independent, as would be if this was just a product. So there is some sort of interaction which is described by this term here. Okay, so this you can apparently write down. But once you have this, there is a sort of a mechanism to go from here to this Fredholm determinant description. It's not a trivial step, but there is a way to do that. Because what you want to do really is compute the asymptotics of this as k becomes large. And you know, there's this product over k appears here, and then the number of integrals is k. So it's somehow inconvenient formula to do an asymptotic calculation. So you have to massage it in a different way. If you go to this Fredholm determinant description, k will appear as just as a parameter, and then you can take asymptotics. So we'll see how that works a bit later on. Okay, so what do you get? Well, out of this, and this is quite a long calculation, you get, for example, if you look at the flow at the origin, it's a function of time. Again, there's a linear drift, so there's a number of particles that there's a net flow to the right or to the left, depending on the parameters of the system. You subtract that because that's the sort of dull behavior. Then the fluctuations around that mean drift are again of the order of t to the 1/3. And moreover, you can compute the distribution of that quantity, and it's again related to Tracy-Widom type distributions, right? So this is, we've heard this several times before. Okay, so what are the main ingredients? Why does this work, and what are the main ingredients? Well, the first ingredient I'd like to emphasize is that this RCEP is a Yang-Baxter integrable stochastic lattice model. So for that reason, you can write down this multiple contour integral. So there is an explicit formula which you would not normally be able to write if you didn't have an underlying integrability structure. So that allows you to do this second dot point. They express certain observables, not all. So it's sort of an art form to find the right observable. For certain observables, you can express the expectation in terms of a k-fold integral using essentially using beta-ansatz type methods. But then you're mostly interested in some asymptotic calculation, and quite often that involves taking k to infinity of large k. K would be on the order of time, and so you have to do asymptotics for large k, and then this formula is not particularly suitable. But there is another trick. You can transform it to a Fredholm determinant sometimes, or most of the times. And then once it's in that form, that essentially you do a saddle point analysis. And then there's lots of finicky details, convergence estimates, and all of that that you need to do to make this completely rigorous. Right? Is that a fair summary of? Okay, so what I want to talk about today is so what are the new things? So far, people have only been able to do this sort of program for a model where you have one family of particles of a particular type. And on Monday, we heard a lot about colored models. So you have particle system with different colors, different types of families. And you'd like to understand asymptotic behavior for such a model. So I'll be talking about a model with two species of particles, and I call this a rank 2 model. It will be an integrable model, so that we need that, which means we can do step 2, but now this integral will have some dynamic poles. So the experts will probably understand what that means, but I will show some formulas of what it means, and that complicates things quite significantly. But anyway, we can do something, and we will arrive at a if you have a rank 2 model, there's two species of particles. Each would have their own sort of current, and basically it's a 2-component model. You have to look at the 2 eigenmodes of your system, and they each have their own distribution. And what we find, the end, that there will be a combination of Gaussian and GOE modes from these 2 eigenmodes. Okay, so here's the model. It was a model first looked at by Arndt-Heinzel-Rittenberg in the 90s. It's an AHR model. And it's sort of 2 TARCEPs put together. There are plus particles that drift to the right with some hopping rate p, and there are minus particles that hop to the left with rate q. And then they can interchange. So if I have a plus to the left of a minus, then these two can exchange into minus plus, but you cannot go back. So basically there are three tarsips here. If you have only plus particles, that is just a tarsip. If you have minus particles only, it's a tarsip but in the other direction. And if the whole lattice would be filled with pluses and minuses, then the minuses would play the role of holes. And again, you have a tarsip, but now with rate 1. So there's three tarsips, but they all have different rates, and you sort of put them together. So here's a space-time picture. I read this from bottom to top. So, you start with some initial conditions, for example. The black dots are the plus particles, and the white dots are the minus particles. And so the white dots try to move to the left over time, and black particles try to drift to the right over time. And so if they don't interact, they just behave like a tarsip, but then they start interacting, so they mix up. But once they've all crossed, they just, the white particles drift further to the left, and the black particles drift further to the right. And so once they've all crossed, they no longer interact anymore. And of course, we're interested now in the sort of flow and flow fluctuations in this sort of region here, where you have a mixture of plus, minus, and holes. Okay, so just one slide on physics heuristics. How do physicists describe this? Well, they think in terms of a continuity equation. So if U represents the density of particles, so it's a two-component vector, the density of plus and minus particles, then the rate of change of U plus the space derivative of the flow of the particles equals 0. So this is a very generic, conservation of mass, basically. But these flows are given by nonlinear expressions in terms of the density. So basically, by a quadratic in the two densities. So the claim is now, so this is a deterministic equation, but it's a nonlinear one. You should add diffusion and noise to this, like with KPZ, and that you should correctly describe in a heuristic way at a macroscopic level the behavior of these particles. This idea or this theory is called nonlinear fluctuating hydrodynamics, and if you do that, start from this starting point, you can derive that the probability that the two families cross completely in time has a distribution which is a product of a GOE and a Gaussian. Yeah, it's like in the picture. It's you have Bernoulli for the plus particles and Step for the white particles. But you can take, of course, other initial conditions, and then maybe this will change to GOE or some other. But essentially, it's this. And S plus and S minus are, this is a two-component PDE, and S plus and minus are the eigenmodes of this PDE. So there's a calculation you can do and that gives you explicit expressions for S plus and minus in terms of the particle densities. So we'll get to that.
So is this computation really giving you the trace Witten distribution, or is it just reducing it to something previous? Because how do you get a trace Witten distribution? You get some pressure.
Well, so from this you get a two-component KPZ type system, so and then you go from there.
You're just saying that we know KPZ.
Yeah. So it's
P crossing of T. Can you explain that again?
Sorry?
What's P crossing of T?
Oh, P crossing is the probability that after time t, from an initial conditions where all the plus particles are to the left of all the white particles,
Finite number of particles?
finite number of particles, that they cross. but in a scaling where the number of particles scales with time to infinity. So there's a certain scaling limit.
That relation on the next slide, that's an asymptotic relation, and some number, and this parameter goes to infinity.
Yeah, this is an asymptotic relation where time goes to infinity, and these s pluses minus are at particular scaling limits.
Okay, you're not saying what the scaling is.
I will get to that. So I'm still at the sketchy level. I'd like to try sort of to create some context before we get to the scary formulas. So this is how the physics works, and so the aim of our work was to rigorously prove this sort of result. Sorry? S plus and minus depend on the particle numbers and time. I will show you at the. It will appear somewhere. Okay, so how do we get there in a more mathematical and more precise way? So we start with the master equation of the process because we are interested in the first step is computing the Green's function for this system, right? So the probability when you start from a certain initial configuration, what's the probability to end up after time t in a certain final configuration? So the Green's function satisfies the master equation, which means that the rate of change of the Green's function has 3 terms. So first of all, these are the hopping rates of the plus particles. So if xi are the coordinates of the plus particles, and xi minus means that the ith coordinate is 1 less, then that particle at position I can hop to the right to position xi, and therefore give a positive contribution to the rate of change of g. Likewise, for the minus particles whose coordinates are y, if the ith minus particle is at yi plus 1, it can hop into yi with rate q, and so that is a positive term, and then you subtract the diagonal terms where particles can hop out of the given configuration that they're in, right? So it's just a Markov chain equation, which you have to solve. And then you can, so this equation is valid where all the particles are sort of isolated from each other, so they don't interact. If they interact, we have an exclusion because 2 particles cannot occupy the same site. So there is an exclusion effect that you have to incorporate, and you can write that as some sort of scattering condition that if I have the Green's function and 2 coordinates are equal, then this should equal the Green's function where the second coordinate is the first plus 1. That just follows from an exclusion principle to make this equation consistent. Same for the minus particles, a very similar condition. And then the scattering, where the 2 particles can interchange, there is a certain condition, namely if the plus particle is at y and the minus particle is at y plus 1, then that value of the Green's function should equal q times having a plus particle at y plus 1 and a minus particle at y plus 1. That physically can't exist, but you continue the Green's function and just put the coordinates equal, plus p times this value of the Green's function, right? So that basically the thing what you need to do is solve this Markov chain equation with these 3 conditions to incorporate the interaction between the particles. And then, so you get a general solution, and then you still need to fix the initial condition that at time 0, all the particles are at their initial conditions, x0 and y0, right? So you can do that because this is an integrable model. So there's a way of making some trial guesses for the functional form of the Green's function in terms of plane waves. And this method is called Bethe-Ansatz. And because it's an integrable model, you're more or less guaranteed that this works. If you take the right linear combination, it's easy to see that plane waves will solve this equation, but the difficulty arises in how to satisfy these sort of interactions. But it's doable, and we have to generalize the normal Bethe-Ansatz, and it's something called nested Bethe-Ansatz. So what do you end up with? Here is a formula for a very explicit formula for the Green's function that I'd like to explain. So it's valid for the following case. We first take as initial conditions that all the plus particles are to the left of all the minus particles, right? So they are fully separated. And we take the condition that, the final condition that after some time t, they have fully crossed, namely that all the plus particles are to the right of all the minus particles, right? So I start like this and I end up like that after some time t. So what is the probability of that happening? Well, the probability is this formula here. So we have to go through this step by step. If you look at the blue bit first, that would be the formula if you just had a tar-sep, like a single species tar-sep. It's determinantal, and you have to integrate over these z variables to satisfy the initial condition. So it's determinantal, and that determinant takes care of this exclusion principle, right? Because it's a determinant. If two coordinates would be equal, the determinant would more or less vanish. That's sort of the exclusion part. If you look at the, what is it, brownish bit here, that's again a tar-sep, but it's now just for the minus particles. So if you have only minus particles, the Green's function would be this determinant here. And that takes care of this exclusion principle. But because, of course, we have a mixture of plus and minus particles, we just have a product of these two determinants. And if they would not interact, that's all you would get. But because there is an interaction, we now have to add something for what happens if the plus and minus families interchange, and that's this red bit here. So every time you have an interchange of a plus and minus particle, you get an additional factor that looks like this, 1 over qz plus pw. And then you integrate over all z's and w to satisfy the initial condition. So this factor here, this red product, implements this third scattering type of relationship. And the integration implements the initial condition. Okay, so it's a bit of magic, I guess, that you're able to solve this explicitly and write down explicit formula. But you can, and here it is. And I forgot to mention this e to the lambda t. So this lambda is a formula that looks like this. It's again expressed in terms of z's and w, and it's basically the eigenvalue of the transition matrix or generator of this process. Okay, so there we go. This is a sort of scary formula 1. It's a fully explicit expression. So I hope that was clear, more or less. Okay, so how can we use this to compute this current distribution, for example? Let's start with the simplest case of a step initial condition. So let's prepare the system in this way, where we have n plus particles to the left of the origin and m minus particles to the right of the origin. And now we're interested in what is the probability of the time t that I have crossed. So to compute that, I take the Green's function and then sum over all final coordinates. Right, so I have a lot of sums of all the final coordinates, where the pluses are to the right of all the minuses, over my Green's function with these initial functions. So if you compute that sum, you end up with a formula that is that has a factorized kernel. This is not obvious, right? So we start out with a Green's function that has determinants in it. If I now sum this particular observable over all the final coordinates, I end up with something like a multiple contour integral, but now the integrand is completely factorized, which is nice because that allows us to do asymptotics. Again, so there's van der Monde factors in here. There's some powers of z and w, and then some poles at 1.
So is it based on some polynomial identity involved with determinants?
Yeah, it's sort of the usual type of identities. That basically it's a similar identity that you have in TASEP. In this case, yeah. The only difference with TASEP is that, so if you don't have the red bit, it looks very similar to TASEP. Actually, there's a limit to TASEP, which I'll show next. This is the interacting bit, right? So you can see you have to do these contour integrals where the contours are around the origin. But the origin has an issue because of this e to the lambda t here. If you remember, lambda is a sum over 1 over z. And so if I have e to the lambda, so it's basically e to the t divided by zi, that has an essential singularity at the origin. So it's a bit difficult to compute the residues there. So what you have to do is to form the contour to go around all the other poles. And so there are poles at 1, they are easy. But now, if I integrate over z's, the z's have poles in where the w's are. And then I have to integrate over those as well. So that's what I meant with dynamic poles. The poles of one integration family has poles in the other. And somehow you have to deal with that. So these poles move around as you integrate. So somehow I have to deal with that. So, as I said, this e to the lambda t produces an essential singularity at the origin, and so you need to deform the w contours to lie around other poles. Now, there are these dynamic poles, but for this particular initial condition, it turns out that they don't give a non-zero contribution, and only the simple poles at w equals 1 give a non-zero contribution. And then you can integrate, because these poles you can integrate 1 by 1. Because the poles are simple, so there's just very simple residues, and you can integrate out of the w variables, and you end up with a simpler formula that looks like this, where you integrate just over one family, and basically that's a TASEP type of distribution. So there's a sort of with some details, you can show that this is equivalent or exactly the same as the proper like a current distribution you will get for TASEP, where you have one family. And it's not a surprise, because if you go back to this initial condition here, so if I'm going to go into the limit where I have a large number of plus particles and a large number of minus particles, these holes will just disappear, and I just fill my system with pluses and minuses, where the minuses will now play the role of holes, and the pluses are the particles. So I just have only pluses and minuses, and that's a TASEP. So I should get TASEP for these particular initial conditions. And I do. And then you can, there's a well-known, well-published analysis that Patrick also referred to analyze this further. So, so those initial conditions were too simple, so that's why we want to go to this particular step Bernoulli, mixed initial conditions, where the plus particles are prepared in a random way, and the minus particles are in step initial condition. And so the distribution here is exponential with parameter rho prime. So you can do that, and then if you then compute the total exchange probability, it's a very similar formula as before. The only change is now that there is this rho prime appearing in the denominator. So the zi's will now have a pole, an additional pole at 1 over rho prime. And now we want to analyze this expression as time becomes large and as n and m become large. in a certain scaling limit. So n and m, move with time in a certain described way. And so you can imagine that this is not quite the right formula to do that, because you have to integrate over n and m variables. So the asymptotic limit you're interested in just means you have to compute more and more integrals. Nevertheless, you could do this if n is larger than m, but and there's sort of a straightforward way to do it. But it's actually not an interesting case. The more interesting case is when n is less than m. Now, so why is that? If you look again at this picture, so the plus particles are distributed randomly, which means that on average they're further away from the origin. So you're interested in sort of timescales where they meet at the origin. So if I have more particles, more plus particles than minus particles, at long times they will have crossed, and you're still left with plus particles that still need to sort of cross the origin, right? So you're in the wrong scaling limit. What you need for them to sort of cross at the right time together at the origin is that you have less of these, so that the average distance from the origin is the same as that of the minus particles. So number of plus particles needs to be less than the number of minus particles to be in an interesting scaling regime. And that's precisely the case where this integral is not easy to evaluate, as expected. But it makes it interesting. Okay. So what's the type of scaling limit that we be looking at? Well, this heuristics physics theory, nonlinear fluctuating hydrodynamics, suggests that the scaling form should be like this, where the plus particles have a mean drift given by a current, J1, and then the drift is linear in time, and that there are corrections of the order of t to the 1/3 and t to the 1/2, or rather there could be corrections of this form, and the same for the minus particles. And all this J1, J2, alpha, beta, gamma, delta are known functions of the model parameters, right? They're not unknowns, they are just known. I didn't want to write them because they're clumsy functions, but easy, but cluttered. So what we need to do is insert these type of scaling formulas into our formulas and see that there is a self-consistent asymptotic analysis. So what we need to do is analyze a formula of this form where you have n times m n plus m integrations, where n and m become very large in this particular way. So this formula is not suitable for that, and you have to go to a Fredholm determinant. And so it turns out that you can write this as a regular determinant. Say m by m is larger than n. And then there is this trick that if you have a determinant of 1 minus ab, where a and b are matrices, then you can swap the matrices, and this is just linear algebra. This is the determinant of 1 minus ba. But a and b are sort of rectangular matrices, finite in one direction, infinite in the other direction. So once you swap them, you have basically like an infinite determinant, if you like. So there's a way to do this precisely, and you end up with this Fredholm determinant. Now, once you're in this form, the particle numbers n and m, so these guys, n and m, appear inside the product BA just as parameters. No longer are they related to the dimension of the matrix. So once you're in this form, there's some hope you can do asymptotic analysis. Okay, so I just want to sketch, so there is a program to do this. So if you have, like, this is the usual RCEP type integral. So in view of the time, I'm just going to skip this. You end up with a Fredholm determinant with a certain kernel k. And that k can be written as a sum over simple functions phi and psi that are given by these formulas, right? So this is just a straightforward calculation that you can do. where phi is a contour-integral of a single variable around 1, and psi is a contour-integral of a single variable around 0 and -1. And I just have this simple form. So you can see from this simple form, in here, you can just estimate these integrals using steepest descent type methods, right? If n and k and t are large, you just write all of this as one exponential, and you do a steepest descent. So that's what you need to do. You need to insert the scaling limit for n and m that we had before, how they scale in time, insert it in these formulas and do a self-consistent steepest descent. That steepest descent calculation is well, it's somewhat advanced, but a straightforward technical calculation. What you also need to do now is show that these guys converge uniformly for bounded values of these coefficients kappa 1 and psi 1 that appear in the scaling ansatz. So there's some quite subtle calculation that you need to do here. You need to bound them when kappa 1 and psi 1 are large, and you do that for both phi and psi, and then you can compute the scaling limit in this certain way, and then you can do steepest descent. So here's the detail of steepest descent. You write phi as just, you put everything in the exponential. So now this function f has this particular form. So, which just means that it's the same phi as I showed you before. All these logs come down as rational functions. And then you have to integrate around the pole at 1, but you have to integrate along a very specific contour to show uniform convergence of this steepest descent on that contour. So there's some subtlety involved. Okay, anyway, you can do that. You'll find that there is a saddle point, which I've noted by W star here. And that's actually a double saddle point, which implies that if you expand f around that saddle point, you get a constant term and a linear term and a cubic term, and the quadratic term is 0 because it's a double saddle point. So if you do that expansion, then the time parameter comes in as t to the 1/3, and t here, and then the other terms are lower order corrections. And so you see that if I scale the distance to my saddle point as 1 over t to the 1/3 with some scaling parameter nu here, then this becomes linear in u. So w minus w star cancels the t to the 1/3 on this scale. And this cubic term cancels the linear time on this scale. So both of these get cancelled. This becomes linear in u. This becomes cubic in u. And so you end up with constant times time plus nu cubed plus a linear nu times some parameters plus lower order corrections. And so the function appearing in your exponential has this particular form, and that leads to an airy kernel. So the standard formula is then this phi in the right scaling form becomes this e to the f evaluated at the saddle point times time times an airy function because of the scaling. So the fact you get an airy function is because the saddle point is a double saddle and there is no quadratic term here. If there was a quadratic term here, you'll get a Gaussian. Okay, so that's the usual method, and you end up with this sort of statements that your Fredholm determinant converges to a determinant with an airy kernel. And from there you get the GOE distribution or similar. Okay, so just what are we faced with? We have a formula that looks like this. So there's an integral over z variables, and there's an integrand that just depends on the z's. And then there is an integral over w variables with an integrand that just depends on the w's. But then there is a bit that depends on both families, and this bit doesn't factorize. Well, it's a product, but it doesn't factorize into something only depending on z's and something only depending on w's. Right? So this is not a product of two integrals. It's sort of the W integral sits inside the Z integral. And now we have to analyze this. And if you try a similar method, you find that if you would just consider the W integral, if I would just naively follow the same process, then you get a Fredholm determinant for this integral here, the second and third line, with a kernel that still depends on the Z variables that you still need to integrate over. And these phi and psi functions, they also now depend on these Z variables. But what happens is, so if you look at this formula again, so while if I do that, I still have to integrate over the Z's, but the Z's are located around the pole at 1. So the Zi's are close to 1. Now if you analyze this kernel here, there's a statement that says that that kernel is the kernel with the Z's equal to 1. So now you have a kernel where there are no longer Z's appearing, it just depends on the W's, times some correction terms that are linear in the Z's. And that's it. And this allows you to estimate this second term, and it turns out, and this is, we are working on this, that this term is exponentially small compared to that term. And so we'll find that asymptotically, this sort of nested integrals actually factorize in the large time limit, plus corrections that are small. And the subtlety lies into making this completely rigorous, showing that these are small, but we're almost there. So. Okay, so once you have the factorization, once you can approximate this kernel by that kernel, then the two integrals factorize, and you can do the usual thing. And so this is my last slide. You end up with that this crossing probability that we expressed as this big contour integral using integrability, ultimately in the long time limit factorizes into a GOE and a Gauss distribution with parameters that are defined by scaling limits. So here are the formulas for those S plus and S minus in terms of N, M, and T. So they're very explicit, they're just a bit ugly. Okay, so and then you can just plot in, as a function of the particle models, you can just plot the full distribution like this. Okay, so I hope I sort of given you a conceptual and some details of our proof of this nonlinear fluctuating hydrodynamics for a two-component mixture of particles. Just want to emphasize that we heavily rely on the integrability of the model. And now there are many integral models. We saw a lot of integral colored particles models, so hopefully this sort of process can be repeated for all those colored models. And generally you would expect a mix of Gaussian and KPZ modes. It could be that your system is degenerate, right? I spoke about the two eigenmodes of a two-component system. It could be that your eigenvalues of your continuity equation are the same, and so you have a degeneracy. So it could be that there is a certain scale where these modes start to mix, and you can't really distinguish them, and then there would be something new there. It'd be interesting to see if that could happen if you play with model parameters. And I would like to emphasize that the main technical difficulty lies in treating of these dynamic poles. So we hope that we end up with some formalism where that can be done systematically also for other models. And so thank you.